Drilling fluids touch just about everything in the drilling process. We're here to deconstruct the drilling process and drilling fluid concepts to provide a deeper understanding of our industry. In each episode, we'll share information, talk to interesting people, and maybe share a few stories along the way. Welcome to the Flowline, a production of AES Drilling Fluids, brought to you by Matt Offenbacher and Justin Gauthier.
Welcome to this week's episode of the Flowline. We have an awesome guest today and something we've been talking about for a long time. Matt Offenbacher and I somehow managed to get the legend, Mr. Fred Dupriest, on the show. Mr. Fred, how are you doing this beautiful day?
Oh, I'm doing great, and I really appreciate you guys having me. I'm looking forward to it.
Awesome, Matt. Well, I'll let you go ahead. Matt, how are you doing today? I know, Astros are doing well. I know you're in good shape right now.
I don't have anything to complain about other than maybe Greinke having a rumored arm soreness, but we'll see how Urquidy does today. But all that being said, we're really excited to have Fred Dupriest joining us. I'm going to give a little bit of a personal background as long as it's professional. If you've ever sat through a mud school I've taught, and I tell you other resources to look at, I give you names of who's who of papers you should read. And Fred, your name is the first one that I suggest as far as drilling engineers trying to learn something. I call it required reading. And I know you used to work with a gentleman named Paul Pastusik. Is that correct? So Paul was good friends with my dad years ago. And when I was looking at possibly trying to find maybe join an operator as a fluids advisor or something, like I get an idea of what a subject matter expert could do for an oil and gas company. Paul agreed to meet with me. And he said, if you ever do this, this is one of the most impactful things that could happen for you, is if you join the organization, have the person who brought you on introduce you and say, this is the person, this is my guy, this is my gal. I trust them, and I hope you welcome them into the organization. And that will help you add immediate value. He said that was one of the most important things that happened to me when I joined ExxonMobil. And he was talking about you doing that for him. And that's actually something that I've always tried to be very intentional to do when I hire folks or new folks join our organization now. So you probably didn't know that, but what goes around comes around.
I would actually turn that around and say, if you ever leave an organization and want your work to be sustained, go find the best person in the world at it who spent the last 20 years teaching you how things work. Now, Paul, as y'all know, Paul just was awarded the Drilling Engineering Award for this year from the SPE, and there was never a more deserving person. I was stunned that we were able to hire him. So, you know what? There's a story that works both ways there.
Sure. Great people collaborating together for sure. If you don't mind, I'll just for our audience. So Fred seems pretty well known, as we keep saying. He retired in 2012 as the chief drilling engineer after 35 years with ExxonMobil. During that time, he developed new drilling practices to improve performance that are now taught and used all over the country, including what's called the Limiter Redesign performance management workflow. You can read all kinds of papers about this. But after retiring 8 years ago, Fred became a professor of practices at Texas A&M University, where he's taught classes on physics-based high-performance drilling practices. And he also continues to work with operators to move their organizations towards those same physics-based limiter redesign practices, some of which he'll be discussing today. Fred is a recipient of the SPE International Drilling Engineering Award, a distinguished member of the Society of Petroleum Engineers, and an inductee in the American Association of Drilling Engineers Hall of Fame. So if we don't have enough nice things to say about you, Fred, everybody else in the whole industry does. So we're really excited to have you with us.
Thank you, Matt.
With that said, Fred, take the stage and rock and roll, sir.
Okay, well, of course, I do have a persistent focus on a workflow, limiter redesign, which is a physics-based approach to whatever limits our performance. And I'll go through that. Now, what I wanted to do with the fluids group like this was just kind of give a couple of examples of how that plays out on fluids issues. Much of the work that we've done has been around mechanical specific energy, bit dysfunction, vibration management, and you imagine a bit trying to cut rock. But the fluids can be in a certain situation can be a very dominant limiter, meaning they are constraining how fast we can drill, or the footage per day, which is really a better metric to use. So let me just dive right into the limiter redesign process. And it arose from really trying to understand the physics of how bits really work. And in the end, it evolved because we realized that everything worked process-wise similarly. So the way a bit works is that we apply weight on bit. And as we do that, the more weight you apply, the more it indents. It just indents. If I double the weight on bit, it indents twice as much now. And so I drill twice as fast. When you start out with a low weight on bit, you're actually indenting the chamfer on the edge of the diamond. So it may not be quite efficient, but once you get that buried and you keep applying weight on bit, you truly do get this linear response. Can you guys see my cursor?
Yes, sir.
Okay, it doesn't always work in Zoom. So you get this linear response, double the weight on bit, you get a proportionate increase in ROP. So ROP is easy. You just keep raising weight on bit, right? Well, what we know better than that from our experience is that something happens and we raise weight on bit and we don't get more ROP. So as what happened here was we kind of discovered mechanical specific energy, and we now had this tool that would tell us when we were linear, MSC doesn't change. You keep raising weight on bit, MSC stays about equal to the confined rock strength. If you come off that straight line, then it's because there's some dysfunction occurring. So put that together and it suggests a workflow. I raise weight on bit and I watch MSE. And as long as MSC stays uniform and low, I don't really care about its exact value. It turns out there's a lot that can affect that. But if it's, 7,000 pounds, 7,000 PSI, 7,000, I know that I'm on a linear slope because MSC is really the ratio. It's really kind of tied to that slope. As soon as MSC goes up, I know something is going wrong. Well, then you do the research, what can cause the bit to not perform, and this is it. There's 4 categories of things, and of course vibrations includes oral, stick flip, and axial. So there are subcategories of these things, but there's really just 4 buckets, and you go out and you figure out all the physics and you say, well, if that's the physics of how it works, then what should I do? I'm going to go out and I'm going to raise weight on bit until I see MSE jump. How do I figure out which of these it is and what should I do? And for everything, it turns out we already knew the answers, everything. And we knew those answers in the 1990s. What we really lacked was a process for raising weight on bit, analyzing, and we kind of lacked MSE, something that made it obvious. So with this, I start to become deterministic, foot by foot by foot, what limits me, because I can run this weight on bit step test anytime I want, as formations change or whatever. Before that, what I'd have to do is raise weight on bit, drill 5 wells and see which one drill the fastest. And in reality, so many things change that you never really have a controlled experiment. So MSE was big. And the other thing that we realized, understanding now how bits work, that you really have this linear response, is that we don't fix dysfunction. Now, this curve you're seeing right here that I had plotted is the classic shape of bit balling, which have lots of fluids responses, So when you have bit balling, I come off the line, MSE comes up, and the more weight I put, I may end up drilling almost 0 ROP if I keep going up and up and up on my weight on bit. That's that characteristic shape of that. Whirl actually gets better. I would start low, at low weight on bit, I have high whirl, and as I increase, I move closer to the line. So the different dysfunctions over here, there's a lot to learn about how to use MSE, but the basic principle is the same in that I don't fix a problem, I extend the weight on bit at which it will reappear. So for bit balling, if I have bit balling at 20,000 pounds weight on bit and I increase my bit HSI, I'm still going to have bit balling, but it's going to be at 40,000 pounds weight on bit, and I'm going to be drilling twice as fast. So it's a real important principle of bit mechanics, that the bit wants to live on that line, and it will if you let it. If it's not living on that line and you fix it, you're not going to, you just come back to that line. You can't do better than that line. So for example, if my weight on bit is down here at a weight in ROP where I don't have bit balling, increasing the HSI won't do anything at all for me. Does that make sense?
Yep.
So this idea then kind of translates to limiter redesign. We don't limiter fix. We don't fix a problem. We redesign the limitation of weight on bit, or RPM. RP is linear with both, so we can drill faster. Well, so where we start to get into more fluids issues is that lots of things can limit us from running weight on bit. You literally go out and raise your weight on bit and step tests and watch and see everything. You're watching everything. And if I run out of motor differential, I'm done, right? I never get to bit balling. I never get to stick slip. I never get interfacial severity damage. I start raising my weight on bit. And so what do I need to work on? Well, go get a higher torque motor so I can run more weight on bit. So if I double the torque rating of the motor, I basically extend it. It's still going to limit it. And so now I drill twice as fast. The thing about this, what this illustrates is that I would say in about 80% of all footage worldwide, we're not limited by the bit. We're actually limited by what we call a non-bit limiter. And the motor differential, in the unconventionals is, we're always pushing that. And for example, but if I really understand the physics of motor differential, it turns out I can get a lot more. So why are we using super high torque, low speed motors when we're not using but 20% of the torque capability? Why not go high speed? Because my ROP is linear with RPM, just like it is weight on bit. And I can get a higher speed motor with more torque than I'm actually using and drill twice as fast. So there's what we would say is there's a physics to every limiter out there. And the first step, is identify what limits you. And you do that by raising weight on bit until you observe something. But the next step is to go try to find some new knowledge, because if you make your decisions, your next decision is based on what you already know, you're going to keep making the same decision you're already making, especially if it's empirical. If you say, but this is the motor everybody uses, we don't have any experience with other motors, and there's a risk. Well, but if I really looked at that motor data, I might see spiking pressures, and I'm actually, to keep the spikes low, the driller's actually backing off on weight on bit. And they're running at 70% of motor rating instead of 100% because of the spikes. I bet depth of cut control, and I can run at 100%. There's a level of physics to everything that people don't tend to know, or they just haven't peeled the onion to that level yet. So if you really get committed to limiter redesign, your organization does, you really get committed to going and finding new knowledge, not using the knowledge you already have. And that's part of the workflow that you have to create. So bit balling is a fluid related thing, can be. Other cuttings transport is probably the second really common, obvious fluid thing that is directly on this line. Other things are more subtle, like filter cake buildup is causing us to ream, spend rig time reaming. You don't want to use footage per day as your metric, not ROP. So other things that fluid gets involved in is your reaming time, your circulating time to clean the hole, and your tripping times if you're fighting filter cakes on the way out of the hole and doing those kinds of things. So there's a very direct, I'm going to go do a step kind of process. Those step tests have to be introduced into your organization because none of your organizations are doing that. And it's so fundamental to this whole process of moving forward. And then secondly, there's the more subtle things that aren't directly on this line, where we really have to say, all right, I'm reaming filter cake. What limits me from eliminating reaming of the filter cake? Now, there's a physics to that, and it turns out it has nothing to do with your HTHP. Almost never. It has everything to do with how you use your stabilizer, whether you have stabilizers on your string and how you use them. Who knows that? What fluids engineer is taught the physics of what a stabilizer does to a filter cake and how to enhance what that stabilizer is doing to your filter cake. I actually play between how I design my fluid and what I do with the stabilizer, if I really understand the physics of that. So again, identify as an organization and commit and say, I don't know enough, or I'd already be doing it.
All right.
Yeah, so I think these are really, I've just described some of the key elements. In the end, all your limiters kind of have to lie on the straight line. You're never going to drill faster than that for any given weight on bit, because that's as good as the bit can cut rock. And there's a long physical story to that. But reaming, circulating, and tripping, they're a little bit more of a notional application of because you're not doing a direct test. You're observing everything that's going on in your operation. So I'm going to come back to this later, but we don't get a different result unless we change how someone works. Well, let's see. What makes this challenging here is that there's nothing broken about motor differential. When I'm at a motor differential, no one says I have a problem. We don't record that as trouble time. We don't even talk about it in the morning calls. If you say, how fast can we drill? You say, well, about 300 feet per hour, and we're off. That's it. So almost everything that really does limit, like I say, 80% of it is not the bit. The limiters that we have out there are auger capacity, shell shakers, blinding, in certain sands. But they do it all the time. So almost all of our limiters are what we call normal. They feel normal. They look normal. Had a rig supervisor in a kind of a special training class we were trying to move limiter redesign into other areas. He used to be in drilling. And we were talking about platform in California, and we had just changed a little 9-inch section of auger out. You have a 12-inch auger, it comes to a bulkhead, and it's necked it down to 9 inches to go through the bulkhead, And if we try to drill faster than 100 feet per hour in this long extended reach 12 1/4 holes, that 9-inch section would pack off. And I knew that we had that, problem, and it took 3 years to get it fixed because of permitting and all that, to change a bulkhead. So I had this guy, and I said, well, you used to work in drilling, right? Yeah, I worked that platform 20 years ago. And I said, well, what limited you? And he said, well, we had this little 9-inch section through the bulkhead that would pack off at 100 feet an hour. 20 years we had stood there and stared at that. The day we changed it, we did 300 feet an hour, and every single 12 1/4 extended reach well has drilled 300 feet an hour since then. That's stunning. But these stories are everywhere. I know one project that was over $1 billion behind because of the auger size. And no one did anything about it. We changed the operator, and we took over from another operator because the partners were frustrated. And the very next well, we're drilling 4 times faster. So remember, as a fluids person, looking at how you work and what you think, you built into yourself certain expectations, and they're all based on experience. Unless you go get the physics of the thing and learn something that you don't already know, you're unlikely to make a different decision. You're not a bad person. You're applying everything you know. You've got to go find something you don't know, or you'll continue to do that. And SP papers are typically not great at saying, here's some physics and how it affects operations. So I'm not pretending that that's an easy thing to do. What needs to happen is your whole organization needs to start going into their limiters and researching. And once you research and get an idea, you do field trials, you prove it out, and you make that part of how you work. You build that into how you work. And that takes some time, and I would say that I teach 134 practices in the class that I've taught. And every one of those, I teach the physics, what the driller can see, do, decide, and what the engineer can redesign. Physics, what the driller can see, do, decide, and what the engineer can redesign. each company basically needs to build that. It's how you get the technology in the hole, and if you don't get in the hole, then whatever you know doesn't make any money. So, but once you build that, and I would say those practices took about 4 or 5 years to build. And the last year I was at ExxonMobil, and they've continued to expand, but it takes time and commitment over a long period of time to build training and knowledge and how you get it in the hole. Okay. So this is about how you get it in the hole. You've got to change how somebody works. And if I have knowledge sitting in the office, it does nothing, right? You need to commit to teaching people at the rig site physics that we have never taught them. And mud engineers should have vastly more rock mechanics knowledge, for example, than what we give them, because they're so integral to the rock mechanics solution. So the process is, you do need to identify the limiter, and the organization needs to develop a physics-based understanding, one limiter at a time. And the deeper you go and the better you go, the more differentiated your performance is going to be as an organization if you share that knowledge and turn it into an actual application in the field. In every instance where we're actually raising weight a bit and we run into a limiter, every well, every foot, it's all going to be different in risk. What I want to raise mud weight for stability. Well, what are the risks of raising mud weight? It turns out that everybody knows what's limiting, and they're not making that change because of perceived collateral risk. It's usually another entry. So I want to raise mud weight for stability, but what happens? Oh, we can't do that because of differential sticking. So I don't need to work on raising mud weight or the knowledge of stability. I need to eliminate differential sticking. And of course, we wrote a paper on that in 2007 or so. And I think ExxonMobil has literally completely eliminated differential sticking from its rod operations at almost no cost. That's a paper you might want to look up. But that's the way you make that. That's so critical, because it's got to be the crew. You got to say to the crew, what risk do you see? Because they're the ones that are going to do what you want or not do what you want. And you're going to find out, if you haven't taught them the background physics on it, that they're going to be empirical. They're going to say, nobody runs more mud weight than this. Or, 5 out of 30 wells get differentially stuck. So they're being statistical from experience because they don't have any physics-based understanding. And the reality is that 0 out of 30 wells get stuck if you do the right things. So all of this works together. The one reason to ask them, what risk do you have, is because they know and you don't. Engineers that sit in the office and think they know what these collateral things are. You can see the primary thing, usually, but you don't know the collateral thing that the person is actually afraid of. And if you don't deal with that, they're not going to change the way they work. And if they don't change the way they work, you're not going to get a different result. They won't implement it. They won't raise their mud weight. They'll tell you, you're very cute sitting there in your office and all brave and everything, telling me what to do. And they'll be right. Okay. So whatever risk they tell you they have, do something about it. Now, if they just misunderstand something, explain it. But if there's a real risk, like differential sticking, because of their practice, change the practice. Say, I appreciate that. We're not raising mud weight. I'll get back with you when I've eliminated by design and practice, and there's 7 different things you need to do. Then we'll raise the mud weight. So number 3 is maybe the most important thing, because it ensures you do number 2 in the end. Don't ask people to do what their management doesn't support. So you're a fluids engineer, fluids specialist, you're a consulting fluids company. You talk an engineer into doing something, maybe you talk a rig into doing something, but if it's controversial and the ops or the drilling manager don't understand it, you need to set up a meeting. You need to understand that, know that, and set up a meeting with their bosses, or ask them, is your boss going to be concerned about this? And if the answer is yes, I don't care if they're in Singapore. We're Zooming anyway. It's not that hard. Get them online and go through and make sure they understand the physics, because they're going to sit there like all drillers today and say, my experience is. The higher level you get into management, the more they're going to sit there and say, my experience is. And the harder it is to get them actually to learn something at a physics-based level because it seems disrespectful. I need to teach you how this really works. So management support doesn't mean they sign a procedure. That doesn't mean anything. It means that they understand what's being done, they're actively engaged in it, and they know that it's a learning process, and they're all in on all those pieces. When you do just tell the rig to do something, be specific and provide procedures. And if you don't, you're going to find that there are misunderstandings about how it works, the physics or whatever, because you've got a 20-year driller. They have a way of thinking about things. That way that they have is going to find its way into your new procedure. And it may be terribly inconsistent or may undo it. Secondly, it's just unfair. Apply weight on bit quickly to make sure you don't have high whirl while slowly raising weight on bit. Okay? Just do it. You don't understand my auto driller. You don't understand the buttons I push. You don't understand the controls in this system. You don't understand the stretching the drill pipe while I'm doing it. You don't, the way you develop a procedure that really works is you sit down with the people who do the work, you walk through it, and they will tell you what won't work. And you build that in procedure and you write it down so that the night crew has the same instructions. And the next rig that comes on, and when they lay the rig down and pick it back up, you can hang that procedure to another rig. And that's how you make progress. And finally, stop using high-level metrics to judge success. Well, we raised mud weight and we had less borehole problems. Well, you probably will if they're due to instability, but you probably won't if they're due to tight hole and filter kicks. There's some other things you can do for that, but not that. The metric needs to measure whether the thing you did worked. So if you're going to raise mud weight and think it's going to stabilize your borehole, watch the shell shakers. Did the cavings go away? I mean, that's a direct observation about whether the thing you're doing worked or not. Some of these things sometimes change in how somebody works. You can achieve that in a phone call, particularly if you've been in a process like this for a while and you've approached a lot of things this way. People get used to it. You pick up the phone and in 15 minutes you go through all 6 things. You kind of achieve them all. And I've seen other things take 2 years. Simplest change. You think this is going to be easy. No, because especially if high-level management has some influence in it and all that. So scale your effort. Don't overwork these things. Scale your effort to what is required to get the person to change how they work. And that's your objective. Not ROP, not whatever. Those things will come if you can create change in how somebody works. Does that make intuitively? I think this probably makes sense, but you're looking at it and you're saying, wow, life is short. I already have a day job. I mean, if you're an engineer or a rig supervisor or even the driller on the brake handle being asked to do all this innovation. My experience, and I've taught literally, more than 1,000 rig hands in physics, and I go through the different limiters in the physics. And my experience has been that they are fabulous. They are the ones suffering and caring about and wanting to be great. They just want to be good at their job and perform. Mm-hmm. Your greater issue is going to be with pure engineers, maybe the opposite, depending on personality. Trying to do any of these things, some people may not work well with that. If that's and then of course someone around the drilling manager level is very often difficult. But the reality is that that's just a limiter too. If you're limited by the unwillingness of a drilling manager to sit down and learn how something works, that's your limiter. And you must take responsibility for that, because who else is going to, if you're the one that want to create change? How you do that, is you just got to be brilliant about it. You have to be intuitive and do all the right things. And as a service company, I know you guys know 10 times more about that than I do. But you can appreciate trying to teach a 55-year-old manager that they don't understand borehole stability. But if you don't teach them that, they won't do the right thing. Okay. So let's use bit balling and cuttings transport as examples to kind of walk through how this plays out. So if weight on bit is limited by bit balling, you're raising your weight on bit and you see your MSC go up and your bits ball. You need to know the bunch of physics around that to know that it's not some other dysfunction, but that's a list of things you can learn. Bit balling happens as if we're in a formation that has several characteristics. It's usually lower strength. It's got a certain water to shell surface area ratio, which makes it what we call kind of sticky, which is not why it sticks to the bit, but it kind of relates. Ribbons form, ductily filled material reconstitutes, shears up. These ridges are reconstituted ductily filled material. They flow up into the dome and they get together and they start to grow downward. They pack into here. They grow downward until they reach the bottom. And now they sit on bottom. These things under downhole hydrostatic head, as you ductily fill rock, it expands. You had these nice grains that were laid down and packed tightly. Now they're unpacked. So you get big pore expansion in between the grains. Pressure drops inside this ductily filled material. I have very low pressure inside. In fact, the pressure can go close to zero. I still have hydrostatic head on the outside. Hydrostatic head then presses against this mass with a very low pressure, and I have essentially a differential sticking. I don't stick to the bit because I'm sticky, and all of these sciences and all these products that claim that aren't really seeing the process right. Some of them work, but not for the reason that they claim, okay? So I've got differential sticking. Well, I can still move it if I apply enough force. And so that happens. I can still drill a bit. This material, though, also becomes very strong. It's held on the bit by differential pressure. It develops strength from having high stress between the grains. I've got 5,000 pounds of pressure out here. I've got no pressure in here. What's carrying all that load? One grain is pressing on another grain with 5,000 pounds of force. And that's where rock strength actually comes from. When we fail a material and we make it move, we have to slide one grain past another. And the more stress I have on a grain, the stronger it is. I can take a pile of sand in my hand, totally unattached, take it down into the earth under the stress at 10,000 feet, and that pile of sand in my hand could have 7,000 PSI of strength. Grain to grain stress is where rock strength comes from. And I do a long lesson on that for all rig people because it's so critical to understand that. Why is it so hard to drill a bridge out of a well bore? It's already drilled material. Why can't I just wash it out? There's low pressure under it and you have head above it. You created stress between those grains. So what happens in here is this gets very strong. It's strong enough to actually carry your weight on bit. So now that weight that should be making this indent is less, and it indents less. And that's why we drill slower. We drill slower because of the strength and the amount of weight that I take off of the cutter tip by having this run on bottom. So if you were to go out, into industry especially among fluid specialists and ask them how balling works, would you get that story?
No, definitely not.
Now, because it's a mechanical engineering story, right?
Yeah.
And it's a soil mechanics story about rock strength and the strength of powder under stress. And it's the more Coulomb circle. It's a bunch of stuff. Well, but if I don't find a way to explain that, I don't actually understand the physics of what I need to do. I know empirically that higher hydraulic horsepower makes me drill faster if I have bit balling, but I don't quite know why. The chemical products that address bit balling, what they do is they're penetrating products. Like you have an ROP enhancer, you put it in at 5%. They are very fine oils. The reason I have this low in pressure in here is that I'm in a water-based mud and this type of clay is very sensitive and it swells, so it seals. So oil-based muds don't ball, period. If you're doing 1,000 feet an hour, you're not going to ball. Because oil filtrate can go in here, pressurize the pore space, and it doesn't cause the clays to swell and seal. I can't get the low pressure. I can't get the differential. I can't be held to the bit. And I come apart eventually. So if I have these penetrating or ROP enhancer, they're penetrants basically, that even in the water, they're able to independently travel through and pressurize. That's what they do. So a citric terpene, for example, just orange oil, will utterly eliminate bit balling in South Texas, even the worst bit balling. Okay. The ROP enhancers that were eventually developed are environmentally more acceptable than that. And they're not so utterly, and it takes more of them, but they're still working the same mechanism. So how does MSC play into this? Well, here's an example of an MSC curve. This is a 0 to 50,000 PSI. Mechanical specific energy is the work or energy being done per volume of rock. It should equal rock compressive strength if the bit is perfectly efficient. So what you see right here, though, is that the ROP and all of this rock at 2,000 feet in South Texas has the same strength. So with a given weight on bit, I should be indenting the same amount, and my ROP should be the same for all formations, whether they're a sand or a shell. There's a little difference in strength, but not enough to really change the ROP a lot. When I see big changes in ROP, it's not because rock strength is changing, because that comes from stress, the amount of overburden sitting on that rock, and all this rock has the same stress sitting on it. So the little differences for stuff we won't go into, but there's huge changes in ROP. I'm 50 feet an hour, I'm 300 feet an hour, 50 feet an hour, then I'm suddenly 50 feet an hour, and I'm 300 feet. Goodness, it's all the same rock strength. It should be indenting. You have to know that. As a driller on the brake handle, you need to know that part of bit mechanics. So even without an MSE curve, I know this isn't right. That slow ROP in all wells is always due more to dysfunction than it is to rock strength. So MSE, though, helps us see that. It should be 2,000 and it's 25,000. I'm drilling at the same drill rate with this weight on bit as if I had 25,000 PSI rock in South Texas at 2,000 feet. It's absurd, right? When you see it on an MSE, it's not magical anymore. It's simply mathematically absurd. And then suddenly my MSE does equal about rock strength and ductile failure. And then it doesn't, and then it does. And of course, this turns out that this correlates with sands, which do not ball a bit because they can't keep that low internal pressure till it penetrates. And these are the shells, the young, active shells we have in South Texas. So this was one of the very first times we used MSC on the rig, but we had done a lot of training already about bit balling and the physics of things. And this morning of this day, I was in the engineer's office because we were piloting things. We had an HSI of 5.2, and every bit vendor for bit balling recommends 4.0, which is nonsense. It depends. Do your step test, find it, make your changes, get that whatever HSI that you can. So anyway, we were drilling and we called the rig and we said we could see this part right here, and we called the rig, and the rig supervisor said, I think I have bit balling. We're balling in all these shells and we're not balling in these sands. And the engineer said, well, and he said, I want to change the nozzles and get more HSI. His idea, because he had training. The engineer said, well, let's do the economics on the trip time and make sure we can make up for it in our ROP. And the rig supervisor said, well, you can do your economics, but I'm pulling this no drilling son of a bitch. We were averaging 160 feet an hour. We'd been drilling in this field for 15 years, and we were at record well pace. At 160 feet an hour, we were at average record well pace. And now he's got a no drilling son of a bitch.
Crazy.
Okay, so we did trip, changed the nozzles. We limited weight on bit to not drill faster than 350 feet an hour. The next well, we were at 500 to 600 feet per hour, but we just had never drilled this fast before. So if you look at what's going on here, we had a way to identify that we were limited, had a limiter. The MSC in this case, it changed, it just changed for the person on the brake handle. It changed their understanding. This is not hard rock. We don't have 25,000 PSI rock. If you'd asked a driller, they would have said, man, these shells are tough and these sands are really soft. The people at the rig site understood the physics of what was going on because we invested in them, the training. The change was engineered. You know, we calculated nozzle sizes, stayed in equipment limits. We just did all the right, engineering work. And we managed the high RP risk. We just didn't go out and do something, wild. We limited it to 350 feet an hour. And because we didn't know if the shakers would handle it, that we could clean the hole. We didn't know if we had gauge hole to help us clean the hole or what would happen. That's if you look at that, you see a lot of the 6 elements that I showed you on the last slide. And this was very early on, and instinctively we knew these were right. But I think we refined that over time and become more committed. There's 4 things here, there's 6 things on that list. So the thing that we come back to is that HSI doesn't cut rock. Hydraulics don't cut rock. And if you don't understand the physics of that, you're going to be out running high HSI where you don't need to, where it's not going to help you. If you're getting a linear response, whether you have MSC or not, you're doing step test, and the RP is going up linearly with weight on bit, you don't, more HSI isn't going to do anything. HSI doesn't cut rock, it keeps your bit clean, so it cuts rock like it's supposed to. More HSI doesn't solve bit balling, it elevates the weight on bit, which is going to occur. So what happened really quickly is that we went from HSIs of 2 or 3 to not even accepting rigs that couldn't put up that kind of more HSI, and a very routine HSI became 6 to 8. And every increment of HSI increased the ROP. Now, in a water base in South Texas at 500 to 600 feet an hour, you're going to start to see bit balling. In an oil base, you don't see it at all. And we use so much oil now that, bit balling worldwide is not the problem it used to be. But every increment of HSI, if you don't run more weight on bit, though, it won't change your ROP at all. It's not to cut rock. It doesn't make you drill faster. It enables you to run more weight on bit, so you indent more without balling. And the indenting more is what makes you drill faster. I mean, is that a common way of looking at it among fluids engineers?
Certainly not.
So that's the effect. We know increased hydraulics, increased open face volume, less blades, more junk slot area, more inhibitive mud, even slight increases in inhibition don't solve balling. They just let you run a little bit more weight on bit. So the question is that little bit more weight on bit and ROP paying for itself? And that's the way we should look at it. To do that, I have to run step tests. I don't go drill 3 wells and see if I drill faster. That's not being physics-based. That's not being deterministic. I run a step test and I see what the founder point is. Where does MSC jump? I add my additive and then I redo the step test. Did the founder point go up or did the founder point not go up? If it didn't go up, my additive isn't working. And I know that right now in 1 well. I don't need 5 wells. I know it right now. And in addition to that, maybe I don't have enough additive. I could sit there right now and add more additive and see if my founder point moves. So the message here is that whatever change we have, we need to invent something that we do next in the field with that change that lets us measure directly, that metric that says that the change we made is actually working deterministically. If you're going to prove that by drilling 5 wells, I'm going to tell you, you're not going to prove anything. But if you can prove it by running a step test and seeing elimination of cavings on the shaker or whatever, then you've got something you can actually believe in and teach. So, there's some other things that affect balling here too. In this story, balling balling is not a huge issue for us. If you get out in West Texas, we are balling in the anhydrites, and very few people know that. But if you watch an MSE curve going through those anhydrites from, I don't know, just below your surface casing shoe for a couple of 1,000 feet there, whether you're in the Midland Basin or Delaware, you've got pretty thick sections of anhydrites that come and go, and then salt and anhydrite and salt. Watch your MSE in that anhydrite, and it pops. It just jumps off. It says balling. And there's almost nothing published on that. We first saw that in Qatar, actually, in the anhydrite there, and did a lot of experimentation on rigs in the field. It showed that HSI elevated the onset of balling to a higher RP in the anhydrite there. Well, so, but most of our unconventionals are in older basins with rock that don't have that right water to shell surface area content to be balling prone. Other than the anhydrites, I would say in West Texas, the rest of the well has no balling at very high weights on bit, 65,000 pounds weight on bit. You know, you're not going to see balling, except maybe in those anhydrites and maybe in the surface hole in some areas. So watch that as well. Anywhere offshore in a water base, which we don't use hardly anymore, you're balling city or South Texas. Coastal depositions. So anyway, think about how you interact to create change. You're a vendor, you're an engineer for an oil company. Change in how the work is done is essential, or you don't get a different result. Think about what these things mean to you and how you would approach them for the change that you specifically want in your case.
Well, folks, that concludes part one of our two-part series with Fred Dupriest. I mean, what a treat that was. And just the amount of takeaway from this first part was awesome. I'm actually going to probably end up re-listening to it a couple times. Matt, what did you think?
I mean, it's one of those where, like you said, you can listen to it every time and you can think about what's holding you back or what's the limitation. So it's like you constantly have to remind yourself, in as much as even if you've heard this message before, you need to hear it again. So I guess that's sort of my takeaway is listen, re-listen. It'll probably affect you differently at a different time.
Excellent. No, I couldn't agree more. So for all the folks out there, I know you're going to be eager for round two. Tune back next week and we'll continue on with the discussion. Thanks again.
Take care.
Thanks for listening. Views expressed in this program belong to participants and not their employees. The program is for informational purposes only and cannot take the place of seeking professional advice. Copyright AES Drilling Fluids.